Hey, hello, welcome. I am Prosper Wong. Hope you've had a nice time through the week. This week we're looking at electrochemistry, just like we saw in our last 2 weeks, where we discussed the ionic theory and defined a lot of terminologies. Now, in this week's lesson, we are looking at something a bit different, a bit more practical, that helps you understand, or let's say, the application of factors that affect preferential discharge of ions during electrolysis, just as we saw in our Zoom class. For those of you that attended the Zoom class, in this week I'm bringing it to you in video form so that you better understand what we've discussed so far. So this week we're looking at the electrolysis of common electrolytes. Without wasting much time, let's dive into the lesson proper. So, considering our objectives for the lesson, what are our objectives for the lesson? Now, what I expect you to learn at the end of the lesson, the first thing is you should be able to describe the electrolysis of common electrolytes. Now, I'm going to give to you some electrolytes, and we're going to look at the electrolysis of this electrolyte. The second aspect, you should be able to state some applications of electrolysis, and lastly, you should be able to describe electroplating and extraction of aluminium by electrolysis. Now, these are topics that some of you may find a bit confusing, but that is only if you've not watched our previous videos. Now, if you've not watched these videos, they are readily available in the Google Classroom. You can always go back to them and visit them, and then do the assignments, necessary exercise that has been given to you. This will go a long way to allow you to enable you understand the lesson proper. So, going into a lesson. Electrolysis of common electrolyte. To understand the electrolysis of common electrolyte, before you could go forward to understanding what I'm going to be discussing, it will be a whole new aspect for you if you don't understand or remember the factors that affect preferential discharge of ions during electrolysis. So briefly, let me remind you of those factors that affect preferential discharge of ions during electrolysis. The first factor that affects preferential discharge is the position in the electrochemical series. Remember, the king Neptune called Madame Alexander for something private. Her car had an accident. A memory aid to help you understand the metal activity series. So you need to remember the electrochemical series and know which metal is more reactive than the next. So remember, I told you that metals lower in the electrochemical series are more likely to be discharged to those higher in the electrochemical series. Second factors that affect preferential discharge of ion during electrolysis, I said, is the concentration of ion in solution. So I told you that if the concentration of one ion which is higher in the electrochemical series becomes higher than that which is lower in the electrochemical series, the first condition would not hold. So we'll go for the concentration. Let's say there are two ions in solution and one is more concentrated than the other. If it is high in the series, it will be discharged only if it is closer in the series to the next ion or to the other ion which is lower. In other words, let's assume sodium and calcium. You know, from the electrochemical series, sodium and calcium are close in the series, but sodium is higher in the chemical series to calcium. So let's assume if calcium ordinarily will be discharged during electrolysis, but if sodium is more concentrated than calcium, then sodium would likely be discharged during electrolysis, something like that. So that's as simple as it gets. And the last aspect is the nature of electrode. I told you there are two types of electrodes: either it is inert or it is active. And we said there are two major inert electrodes, graphite and platinum. Graphite is attacked by oxygen to give us carbon dioxide, while platinum is attacked by chlorine. So that's just a summary of what we did in our last week lesson. So in this lesson, we are going into applying these factors that affect preferential discharge of ions during electrolysis. So stay tuned and stay fixed. First aspect, electrolysis of acidified water. Now, acidified water is water that H2SO4 has been added into it, and this process is usually carried out using the Hofmann's voltammeter. The Hofmann voltammeter is the apparatus used for splitting or determining the elemental composition of water. Acidified water just simply means water that acid has been added to it. The main reason for adding acid into it is to increase conductivity of this water. So H2SO4 is that which is added to it. So before I display what we have on the table, I want you to understand two things. Now, acidified water means it contains two compounds, the acid and water. So two compounds that serve as electrolyte, even though acid is a stronger electrolyte to water, but they are both electrolyte nonetheless. So if you are to split this compound, we're going to be doing this. I'm going to explain this once, and you apply it to every other compound we'll be seeing as we advance. So the acid aspect can be ionized into hydrogen ion and the SO4 ion, that is for the sulfuric acid, while water can be ionized into hydrogen ion and the hydroxide ion. You see, all of this electrolyte has a cation aspect and an anion aspect. That is what you should know. So you should also be able to determine how many of these cations are present in solution and how many of the anions are present in the electrolyte. So that will enable us to understand it. So using the table as an example, I will show you what we do. Now look at this. At the cathode, since hydrogen ion is the cation for the acid and hydrogen ion is the cation for water, hydrogen ion is the only ion that there's likely to be discharged at the cathode, whereas we have OH coming from water over here and SO4 coming from acid. Now hydrogen ion there's no competition, so it is discharged as follows, just like you saw when talking about balancing of half reactions. If you don't know how to do that, I can't do that in this video right now. You can go back to our previous video and watch how to balance half reactions. As I said, without our previous videos, you won't understand a lot of things that we're doing in this video. So take your time. Sometimes it may seem hectic, but if you really know that this is important to you, then you will go back to those videos and watch them, take notes, and it will help you do assignments, whatever is given to you, review it, and it will help you. So in this case also, we're also balancing the half reaction. Hydroxide ion becomes water and oxygen, then electron for electron. This is just a balanced half reaction for both of them. So what do we see at the product? All we see at the product is hydrogen ion being involved, being produced, and over here we have water and oxygen being produced. So observation, when you're performing this electrolysis, what you observe is that there's effervescence, the evolution of the gas at both the anode and the cathode. Now since hydrogen ion is being evolved at the cathode and oxygen is being evolved at the anode, you expect colorless gases at both cathode and anode. So changes in electrolyte. So what happens in the electrolyte? Now, since you're removing hydrogen ion and you're removing oxygen, you are directly removing water, because water is made up of hydrogen ion and oxygen. Now, what are you left with? You are left with the acid. In other words, if you remove water, you are increasing concentration. So, what changes do you have in the electrolyte? The electrolyte becomes concentrated. Now, overall equation, just like we saw in regards to balancing of redox reaction, redox reaction in our previous video. This is how we get our overall equation. Remember, we're trying to eliminate electron over here because the electron on this side is 4, so we multiply all 2 by 2. So electrons become 4. We can easily cancel out. We can look at this 4 electron and 4 electron over here. So this cancels this to have an overall equation. Since hydrogen ion is coming from water, let's consider it's coming from water, and OH is coming from also water. You can join them together since they form the same compound to give us our product, which is water, oxygen, and please you can add hydrogen gas here. I didn't include, that should be a mistake on my side. So you add hydrogen ion to this part of it to complete it. All right, moving on to the next equation. So we're looking at electrolysis of dilute sodium chloride. Now, can you answer the question, how many electrolytes will be present in the electrolysis of dilute sodium chloride? Now, the answer to that question would be water and sodium chloride. So sodium is a cation of the sodium chloride, while chloride ion is the anion for sodium chloride, whereas for water we have hydrogen ion and hydroxide ion respectively. So let's look at the video. The table. So in the table we have hydrogen ion and sodium ion coming from water and sodium chloride respectively, OH and chloride ion coming from water and sodium chloride respectively. So we have the same ions discharge as we saw in the first case. Now the reason for this is because hydrogen ion is lower in the series, so it will be preferentially discharged. Remember, it is dilute sodium chloride. In other words, water is more than sodium chloride, so hydrogen ion will be discharged. Now OH is lower in the series than chloride ion. You can refer to our previous video for the electrochemical series 4 of anions. So we have OH is lower in the series to chloride ion, therefore OH will be discharged. We have the same thing just like we saw in our previous table. In the same way also, you add hydrogen gas to this to complete it, 2 hydrogen gas to complete it. I think that is a mistake, as I said, on my side. Moving on to the next aspect. Electrolysis of concentrated sodium chloride. Remember the first case we said electrolysis of dilute sodium chloride. Now the product will be different if you vary concentration. By varying concentration, the product discharged at the anode and cathode may be different. So in the case of sodium chloride, concentrated sodium chloride, which is also referred to as brine, you have this table over here. The same way you have hydrogen ion and sodium ion and OH ion and chloride ion. But look at this. Even though sodium ion is higher in this, is more in solution than hydrogen ion is still discharged at the cathode. Now the reason for this is because hydrogen ion is far from sodium ion in the electrochemical series. So no matter the amount of the concentration of sodium ion in solution, hydrogen ion will most likely be discharged nonetheless. So it's not affected by the second factor. On the other hand, OH and chloride ion in solution, they are close in the electrochemical series, so chloride ion will be discharged in preference to OH ion because it is more in concentration, considering the second factor that affects preferential discharge of ion during electrolysis. At this point, some of you may be getting confused. Now, to overcome this factor or this challenge, you need to write down the electrochemical series, put it down as I'm speaking in the video. You can pause at any point and look at the electrochemical series to understand what I'm saying. You write the electrochemical series for metals and also write the electrochemical series for non-metals. You can browse it up online, or you go back to our previous video. We have that table in the previous video. So, and look at also the factor. I told you in our previous video that the factor that affects preferential discharge is the peak. That means the most important aspect in regards to this. Now, so in this case, chlorine gas is evolved, whereas hydrogen gas is evolved in this case. So in our observation is a bit different, effervescence at both anode and cathode, but in this case, since hydrogen gas is colorless, you have hydrogen gas being evolved at the cathode, whereas a greenish yellow gas, remember that chlorine is greenish yellow. I remember, see my observation, I didn't say chlorine is evolved, I'm only observing. I'm saying a greenish yellow gas is evolved at the anode and not being specific. Your inference may allow you to be specific, but observation does not allow you to be specific. So changes in electrolyte. Now, since we are removing hydrogen and chlorine, just imagine cancel out hydrogen from here and cancel out chloride ion from here. What you have is sodium ion and hydroxide ion. What is that? What does that mean? It means that the changes in electrolyte, what you have, your electrolyte becomes alkaline, which is the formation of sodium hydroxide. Well, you could say that this is one method for preparing sodium hydroxide electrolytically. So our overall equation will take the reduction half equation and the oxidation half equation, place it side by side. Since our electrons are the same, we have hydrogen ion reacting with the chloride ion to give us hydrogen gas and the chlorine gas. And no, we cannot join these two ions together to give us a product because they are not coming from the same compound. They are coming from different compounds, and so we can't combine them to say, okay, HCl is giving us hydrogen gas and chlorine gas. That will not be the case. Two different compounds, and so we'll let them remain this way. Going to the next one. Electrolysis of molten or fused sodium chloride. Now what this means is just liquid sodium chloride. When you have liquid sodium chloride, it's called molten or fused sodium chloride. In the first case, we have dilute sodium chloride. In the second case, we have concentrated sodium chloride, which is also called the brine. In this case, we have sodium chloride on its own. In other words, you have just sodium chloride. Just imagine melting sodium chloride at a very high temperature to give you liquid, going from solids to liquid. That is what we call the molten sodium chloride. So in this case, there is no competition. We have the sodium ion and we have the chloride ion in regards to the electrolysis, and so we have the table sodium ion and the chloride ion is the only ions present at the cathode and at the anode respectively. So sodium will be discharged, whereas chlorine gas will be discharged. So from this discharge, you can make an observation. So sodium will be deposited at the cathode, whereas chlorine gas will be evolved at the anode. In other words, chlorine gas is greenish yellow. So effervescence at the anode, greenish yellow gas evolved. The cathode becomes larger as sodium is deposited. So what happens to the electrolyte? Since there is no other, that we don't have ions remaining, what happens is the electrolyte depleting. In other words, it finishes. It drains down until it gets to a minimal level. So we're adding the cation aspect, or the cathode, reaction at the cathode, and the reaction at the anode to give us overall reaction. Since our electron here is 2 and we have 1 here, we multiply here by 2 to give us a balance chemical reaction. Remember, balancing of redox reaction. Let me refer you back to our previous video, balancing of redox reaction, to understand this aspect, and that is why it is done. It's a cumulative thing. You can't skip into this video and not miss it, except you understand the previous video. So do so by going back to the video, understand balance of redox reaction, so you don't have problems with this aspect. You can pause the video, go back, or ask a friend to help you out in regards to balancing of redox reaction, and you will be cool. So at the end of the day, we have sodium plus chloride to give us this. So we can, in this case, we can add both of them because they are coming from the same compound. So sodium ion is coming from the same compound, chloride ion is coming from the same compound. What we have at the end of the day is sodium chloride giving us sodium and chlorine gas. Moving on, application of electrolysis. So what are the application of electrolysis? Why do we have to do all this process, go through all the process of performing electrolysis? Is it for knowledge? Is it just to claim that we have amassed knowledge? That is not the case. We're looking at application of electrolysis. Why do we have to have all those knowledge? Well, hold on and stay tuned, and let me take you through the process. The first reason is purification of metals. We're going to see the purification of metals as we advance forward. So we studied electrolysis so that we can use it to purify metals. You can think about why we need to purify metals. Think about it, and you can comment in the comment section. Tell me about it in the comment section in the Google Classroom. So we have the next one is electroplating of one metal by another. This is one aspect that ladies, not just ladies, let's not be biased, both guys and ladies will all benefit from this the most. When you have gold earrings, gold watches, gold these, silver these, electroplated these shiny things you have in your home, most of them, some of them, most, depending on how much of which you have, are electroplated. It has been coated with something shiny, something much that you appreciate more, maybe by gold or platinum or something else. You're electroplating. That is electroplating. We'll come to define it proper. The third aspect is extraction of elements. Now, to extract aluminium, sodium, calcium, and some other metals, you use electrolysis. So without electrolysis, we can't extract this compound. And lastly, preparation of certain important compounds such as sodium hydroxide. You notice in our previous explanation in regards to electrolysis of brine, we noticed that at the end of the day we have sodium hydroxide being produced. So in that case, we could produce sodium hydroxide by electrolysis. Moving on. Let's start with the first one. We're told that we use it for the purification of copper by electrolysis. So now this aspect, if you check previous explanation in regards to electrolysis of common electrolyte, we never discuss the aspect of the nature of electrode. So this is where we discuss the nature of electrode. I do not want to discuss it in that aspect and comfort to discuss it at this point in time. So I'm using a stone to kill two birds. So in this case, electrolysis of common electrolytes talks about the third factor, which is the nature of electrode. Without wasting much time advancing. Now we're told that in this process, the metal to be purified serves as the anode, while the pure form serves as the cathode. Both electrodes are inserted into solution of its salts. Now this point is really important. Note this, they said the metal to be purified serves as the anode, while its pure form serves as the cathode. Now this is a classic wire question, a jam question. You can't afford to forget this aspect. The method to be purified serves as anode. Now I'll show you diagrams to enable you understand this aspect properly. So we have this. Now you have copper anode, and we have copper anode, and we have copper cathode. So we have here acidified copper sulfate. Acidified means they just want it to increase conductivity, but the main electrolyte here is copper sulfate. Now this is the tank, and this is impurities. So in other words, this is the impure copper, whereas this is the pure copper cathode. As indicated here, we're told that the pure form serves as the cathode. Now copper leaves this and is deposited here. After a while, this place depletes, leaving your impurities to fall to the bottom of the container. Now this is because the copper, we're using active electrodes. Copper is our active electrode. Remember, as in our previous video, the explanation is if you dip an active electrode into a solution of this salt, what will happen is that neither the anion will not be discharged. The anion in the electrolyte will not be discharged at the end of the day. Instead, the anode will go into solution and be deposited at the cathode. Do not find this hard to understand. It is as straightforward as I've explained it. So don't create a barrier in your mind telling you, oh, this is really difficult. No, it's as basic as what you see. So the table, we have reactions at the cathode, pure copper, and reactions at the anode, impure copper. All right, let's see what happens. So ions at the cathode, we have, just like we saw, copper ion and the hydrogen ion. Yes, because water or hydrogen, the acid is present there. And ions at the anode, we have SO4 and okay, we have OH, oxygen ion, for one reason or the other, that is added. But what happens is copper ions get discharged. Neither of the anions discharge. Instead, copper ion atoms from the anode loses electrons and enter the solution. Simple as that, as basic as that. So what we have here is this: copper gains an electron and is deposited, and copper in this case loses electron and goes into solution. This is a different way of writing. They're using a negative sign to represent this, and it's almost the same thing. So copper deposits at the cathode, whereas copper ions are formed at the anode. So that is just how the nature of electrode affects preferential discharge. You notice that none of the anions are deposited or discharged. Instead, the anode goes into solution and is deposited at the cathode. Basic. All right, hastening up. Electroplating. Electroplating is basic. So electroplating is a method of coating the surface of one metal with another, just like I explained, giving you gold earring, electroplated gold earrings. It could be pure gold, but most of them are just electroplated. Electroplated spoons, silver spoons, and the rest of them, they're just electroplated. Most are electroplated and not pure silver spoons. So how do we do this? Just like we did in the case of purification of metal, the same way, the anode and the cathode. Now what we have here, let us have something. So our anode is the metal you want to use for the electroplating, while the cathode is the metal you want to electroplate. So let's imagine that this is the precious metal you want to use for electroplating. Let's say this is gold, and then let's say this is iron. So when you place this, your iron as your cathode, whereas the metal to be used for electroplating is placed as the anode. The same way, this goes into solution and is deposited, just like in the case of purification of metal by electrolysis, following the factors that affect, the third factor that affect preferential discharge of ion, which is nature of electrode. So lastly, extraction of element. Now this is the last aspect, and sometimes referred to as difficult by most students, but it is a very, very important wire question which we cannot miss out. I wish you could take your time, pause the video, and memorize or understand this aspect so well. I prefer you understand it so it enables you to always remember, or easily remember. Always remember or easily remember whenever you see questions that pertain to this. So extraction of aluminium. I'm going to be using aluminium. Why I consider this as very important, the extraction of aluminium. I'm going to go through it. It's the same process, the same electrolysis, so it's not going to be a problem. So let's start with this first. The ore of aluminium is bauxite. We use bauxite. It's an impure form of aluminium oxide. So we treat it, the treatment process we're going to learn later on as we advance. Now we use chlorides. We add chlorides to the bauxite we are melting. Let me just make it basic. Now you have bauxite, an impure form of aluminium oxide. So you purify it, remove impurity, you have aluminium oxide. Now you have to melt aluminium oxide, but to melt that is going to require a high temperature. So what you need to do is to add the compound they call the chloride. So chloride is what we have here. You're adding chloride to it to dissolve it, or gives it, or give it the attribute of reducing the melting point. So you reduce melting point of aluminium oxide, and that is why you're adding chloride. And also increase conductivity, just like in the case of acidified water. You increase conductivity and lower the melting point of aluminium oxide, so which bring down the extraction cost. And lastly, electrolyze the mixture using graphite electrode. So it's basic, it's just electrolysis. The first process is just what you need to remember: the ore of aluminium, what you have at the end of the day. Why do we add chloride? Then next, the electrolysis of the process. We're using graphite. So one thing you should know about graphite, remember it is attacked by oxygen. So since chloride is made up of aluminum and oxygen, the oxide is discharged at the anode. So oxide is discharged at the anode, whereas aluminium is discharged at the cathode. It means that our graphite, which is our electrode, is attacked by oxygen. Now what happens when graphite is attacked by oxygen? Carbon dioxide is formed, and so this bar will need to be replaced. Now note this: oxide becomes oxygen, and for electron Y, it reacts with graphite. Look at graphite. Here we have graphite plus oxygen to give us carbon dioxide. That's what the illustration that is being made here. Now purified aluminium ore are dissolved in molten chloride. We've established that already. Now at the anodes, at the cathode, sorry, this is our cathode, this is our cathode. We're seeing here graphite cathode. So at the cathode, aluminium is formed and is collected over here. So aluminium, the same electrolytic process. Now here we have this: due to high temperature, the carbon at the anode reacts with the oxygen and gets burned away. The anode needs to be replaced regularly, and this is all you need to know with regards to extraction of aluminium. Now it may be very, very fast. I may be saying this very, very fast, but I'm going to just add a video to this that allows you to better understand it. So stay tuned. If you don't understand what I've been explaining so far, watch the video, and if you still don't understand, you ask a classmate, and finally you could ask me. So
aluminium is the most abundant metal on Earth. However, it is expensive because a lot of electricity is used to extract it. Aluminium conducts heat and electricity well, has a low density and does not corrode. This makes it very useful for aeroplanes, drinks cans, electricity cables and cooking pans. The aluminium ore is called bauxite. Bauxite is purified to yield aluminium oxide, which is a white powder. Aluminium is then extracted from the aluminium oxide. The aluminium is extracted by electrolysis. In this video, we are going to look at how aluminium is extracted using electrolysis. You should already know how electrolysis works. If you have forgotten, watch our video Electrolysis. How does it work, to refresh your memory. In electrolysis, ions need to pass through the electrolyte, and so the aluminium oxide must be made molten so that this can happen. Aluminium oxide has a very high melting point, over 2000 degrees Celsius. So instead of trying to melt it, the aluminium oxide is dissolved in molten cryolite. Cryolite is an aluminium compound with a much lower melting point than aluminium oxide, and so using this reduces some of the costs in extracting aluminium. The steel case is coated with graphite, providing the negative cathode. The positive anodes are immersed in the molten cryolite and are also made of graphite. Remember that graphite is a form of carbon. When the battery is turned on and electricity flows, the aluminium from the aluminium oxide in the cryolite forms at the negative cathode and sinks to the bottom of the tank. Here, it can then be tapped off as a pure liquid metal. The aluminium sinks because it is more dense than the aluminium cryolite solution. The oxygen from the aluminium oxide in the cryolite forms at the positive anodes. The oxygen reacts with the carbon of the graphite, forming carbon dioxide. The positive anode therefore burns away and needs replacing regularly. This is another reason for the extraction of the aluminium being so expensive. The overall reaction is aluminium oxide to aluminium plus oxygen. Let's have a quick look at the reactions at the electrodes. At the negative cathode, where the aluminium forms, the aluminium ions from the molten aluminium oxide cryolite solution are reduced. This means they gain electrons. At the positive anode, where the oxygen reacts with carbon to make carbon dioxide, the oxygen ions are oxidized. This means they lose electrons. So from this video you should know that to extract aluminium, electrolysis is used. Aluminium oxide needs to be molten for the ions to move through it, and so is dissolved in cryolite to lower the melting point. The anode is gradually worn away because the oxygen from the solution reacts with the carbon of the graphite anode, producing carbon dioxide, and so the anode wears away and needs to be replaced regularly. Aluminium extraction is very expensive because a lot of electricity is needed.
Hey, you're welcome. Hope you enjoyed that video, and it has been fun so far. I'm glad that you understand it, and if you don't understand it, you can come to the Google Classroom and ask questions in a Zoom class. You can ask questions and I will help explain this. Remember, a quick reminder, our Zoom class is solely for questions, so we're coming to the Zoom class with questions or to hear other person's questions, but in the absence of question, we'll just end the class. The videos are meant to instruct you. You're meant to do research. You're meant to answer questions in regards to this, do your assignment and do your classwork. In any case you encounter a problem, you bring it to the Zoom class and we'll trash it out and make sure that every one of us are in line. So thank you very much and do have a nice day. Stay safe. I remain prosper. Mwangu.